Welcome to this scientific lecture on artificial intelligence systems designed to transform passive reading into active capability. We will explore the cognitive mechanisms, computational architectures, and pedagogical frameworks that enable AI to convert information consumption into genuine skill acquisition. Let us begin by examining the fundamental problem. When humans read, they often engage in what cognitive scientists call shallow processing. Information passes through working memory but fails to integrate into long-term declarative or procedural memory structures. On the left, we have passive reading, which leads to rapid information decay. On the right, active learning, which builds genuine capability. The AI interrogation system serves as the bridge, transforming one mode into the other through targeted questioning and forced application. Let us examine the Ebbinghaus forgetting curve, a fundamental result from cognitive psychology. Hermann Ebbinghaus discovered in the 1880s that memory retention follows an exponential decay function without reinforcement. The retention function R of t equals e to the negative t over s, where t is time and s is the strength of memory. This exponential decay is remarkably consistent across individuals and content types. Here we plot retention percentage against time. Notice the steep initial drop. Within 24 hours, approximately 50 to 70% of newly learned information is lost without active review or application. After 1 day, retention is approximately 58%. After 7 days, only 35% remains. This dramatic loss represents billions of wasted cognitive hours annually across the global education system. Let me pose a question to illustrate the interrogation principle. Why does memory decay follow exponential rather than linear dynamics? Consider this from a neural network perspective. The answer lies in synaptic competition and metabolic constraints. Neurons have limited resources. Synapses that are not reinforced through repeated activation undergo long-term depression. The probability of a synapse weakening in any time interval is proportional to its current weakness, yielding exponential decay. Now let us examine the AI interrogation architecture. There are 3 core components: the knowledge extraction module, the adaptive questioning engine, and the metacognitive feedback loop. The knowledge extraction module parses the text and identifies key concepts, relationships, and dependencies. The adaptive questioning engine generates queries calibrated to the learner's current knowledge state. The metacognitive feedback loop monitors performance and adjusts difficulty dynamically. Let us dive deeper into knowledge extraction. Modern natural language processing uses transformer-based architectures to build semantic representations of text. The goal is to construct a knowledge graph. The knowledge graph represents concepts as nodes and relationships as directed edges. Concept A causes concept B. Concept A requires concept C. Concept B inhibits concept C. This graph structure enables the AI to understand logical dependencies and generate meaningful questions. Formally, we represent the knowledge graph as G equals the ordered pair V, E, where V is the set of concept nodes C1 through Cn, and E is the set of directed edges representing relationships. The adaptive questioning engine uses Bayesian knowledge tracing to estimate the learner's mastery of each concept. This is a hidden Markov model where the hidden state is the learner's knowledge, and observations are responses to questions. The posterior probability of knowledge state k at time t given observations 1 through t equals p of observation t given kt times p of kt given observations 1 through t minus 1, divided by the sum over all states k of p of observation t given k times p of k given observations 1 through t minus 1. This is Bayes' rule applied recursively. The system maintains a probability distribution over the learner's knowledge state. As the learner answers questions, the posterior is updated. Questions are selected to maximize expected information gain, targeting concepts with high uncertainty. Here we plot the estimated mastery probability as a function of questions answered. Notice the sigmoid shape: initially uncertain, then rapid learning, finally plateau at high mastery. The AI detects when a concept is mastered and moves to the next. The metacognitive feedback loop is crucial. It is not sufficient to simply answer questions. The learner must receive immediate, explanatory feedback and engage in retrieval practice. Retrieval practice refers to the act of actively recalling information from memory. Cognitive science shows that retrieval practice is far more effective than passive review. Each successful retrieval strengthens the neural pathway. We model this as S new equals S old plus alpha times success, where S is memory strength, alpha is the learning rate, and success is 1 for correct recall, 0 otherwise. Repeated successful retrievals increase S, which decreases the decay rate. This is known as the testing effect. Roediger and Karpik demonstrated in 2006 that testing enhances long-term retention significantly more than repeated studying, even when study time is equated. The act of retrieval is itself a powerful learning event. Beyond interrogation, the AI must force the learner to apply concepts in novel contexts. This is where passive knowledge transforms into active capability. Application questions require synthesis, transfer, and problem solving. We have a hierarchy of cognitive skills. At the base is factual recall. What is X? Next is conceptual understanding. Why does X occur? At the top is application and synthesis. Given scenario Y, how would you use X to solve it? The AI must systematically move the learner up this hierarchy. Let me give a concrete example. Suppose a learner reads about the second law of thermodynamics. The AI progression might look like this. First, factual recall. Question. State the second law of thermodynamics in your own words. This tests basic recall and encoding. Expected response. The entropy of a closed system always increases over time, or remains constant in reversible processes. This confirms the concept is in memory. Next, conceptual understanding. Question. Why can entropy decrease locally in an open system, such as in a living organism, but not globally? This probes deeper understanding of system boundaries and energy flow. Expected response. Local entropy decreases require energy input from the surroundings, which increases the surroundings' entropy by a greater amount, so total entropy still increases. This shows genuine understanding of the concept. Finally, application. Question. You are designing a heat engine operating between a hot reservoir at 600 Kelvin and a cold reservoir at 300 Kelvin. What is the maximum theoretical efficiency? If the engine produces 1000 joules of work per cycle, what is the minimum heat input required? The maximum efficiency is given by the Carnot efficiency. Eta max equals 1 minus T cold over T hot. Plugging in 1 minus 300 over 600 equals 0.5 or 50% maximum efficiency. Work equals heat input minus heat rejected. Efficiency equals work over heat input. If work is 1000 joules and efficiency is 50%, then heat input must be 2000 joules. QH equals W over eta equals 1000 over 0.5 equals 2000 joules. This application question forces the learner to use the abstract concept in a concrete engineering scenario. One of the most powerful techniques is the teaching back protocol. After learning a concept, the AI asks the learner to explain it as if teaching someone else. This exposes gaps in understanding that passive consumption masks. This is based on the Feynman technique, named after physicist Richard Feynman. The principle is, if you cannot explain something in simple terms, you do not understand it well enough. Teaching forces you to organize knowledge coherently and identify missing pieces. The teaching back cycle works as follows. First, the learner reads and studies the concept. Then, the AI asks the learner to explain it back in their own words. The AI analyzes this explanation using natural language understanding to detect gaps, misconceptions, or vague language. Finally, the AI generates targeted questions to address the specific gaps identified. How does the AI detect gaps in the learner's explanation? It uses several natural language understanding techniques: semantic similarity, coherence analysis, and error pattern recognition. Semantic similarity measures how close the learner's explanation is to a reference explanation. Modern transformer models like BERT or GPT generate dense vector embeddings. Cosine similarity between embeddings quantifies semantic closeness. Similarity of e-learner and e-reference equals v-learner.product v-reference, divided by the product of their norms. This gives a value between 0 and 1, where 1 means semantically identical and 0 means completely unrelated. Coherence analysis checks whether the explanation has logical flow and covers all key points. The AI uses dependency parsing and discourse coherence models to detect non sequiturs or missing logical steps. Error pattern recognition compares the learner's explanation against a database of common misconceptions. If the learner uses language associated with known errors, the AI flags it for correction. Let us now quantify the efficiency gains from AI-augmented active learning. We need metrics to compare passive reading versus interrogation-based learning. Metric 1. Retention rate at time t. Measure what percentage of the material is retained after a fixed time interval, such as 1 week or 1 month. Metric 2. Transfer performance. Test the learner on novel problems that require applying the learned concepts in new contexts. This measures true capability, not just memorization. Metric 3. Time to mastery. How long does it take to reach a criterion level of performance, such as 80% accuracy on challenging problems? Here is a comparison plot. The red curve shows passive reading, steep decay down to 30% retention at 30 days. The blue curve shows AI-augmented active learning, gentle decay leveling at 75% retention. The difference is dramatic. Let us do a back-of-envelope calculation to estimate time savings. Suppose a learner needs to master material for an exam. With passive reading, they must review multiple times due to forgetting. Total time for passive learning equals initial reading time plus multiple review sessions. If each review takes 80% of the initial reading time, and 3 reviews are needed, total time is approximately t read times 1 plus 0.8 plus 0.8 plus 0.8. That is 3.4 times the initial reading time. Now with AI interrogation, the learner reads once, then spends additional time answering questions and teaching back. Total active learning time equals t read plus t interrogation. Empirically, t interrogation is about 1 to 1.5 times t read, depending on question depth. So total active learning time is approximately 2.2 times t read. Comparing, passive requires 3.4 times t read, active requires 2.2 times t read. The AI approach saves about 35% of total study time while achieving better retention. Time savings equals 3.4 minus 2.2, divided by 3.4, approximately 35%. This is a substantial efficiency gain, especially when scaled across thousands of hours of learning over a lifetime. Let us examine the neurobiological mechanisms underlying these effects. Memory consolidation involves structural changes at synapses, mediated by long-term potentiation and protein synthesis. Long-term potentiation, or LTP, is a persistent strengthening of synapses based on recent patterns of activity. When a neuron repeatedly fires in response to a stimulus, the synapse becomes more efficient. The change in synaptic weight Wij equals the learning rate eta times the presynaptic activity Xi times the postsynaptic activity Yj. This is Hebbian learning. Neurons that fire together wire together. Active recall during interrogation engages hippocampal pattern completion circuits. The hippocampus receives a partial cue and reconstructs the full memory trace, strengthening the entire pattern. Passive reading does not trigger this reconstruction process. Memory initially forms in the hippocampus, a rapid learning structure. Over time, through a process called systems consolidation, memories are gradually transferred to neocortical networks for long-term storage. Active retrieval accelerates this consolidation process. Another crucial principle is the spacing effect. Distributed practice, where learning sessions are spaced over time, produces better long-term retention than massed practice, where sessions are crammed together. Retention at time t equals baseline retention times 1 plus n times a spacing function s of the review times t1 through tn. The spacing function increases with optimal intervals between reviews. Optimal spacing follows expanding intervals. A common schedule is review after 1 day, then 3 days, then 7 days, then 14 days. The intervals expand because each successful retrieval strengthens the memory, allowing longer intervals before the next review. The AI interrogation system can dynamically adjust spacing based on the learner's performance. If a concept is mastered quickly, intervals expand faster. If the learner struggles, intervals remain shorter with more frequent practice. Another powerful technique is interleaving, where different topics or problem types are mixed during practice, rather than blocking them. Interleaving improves discrimination between concepts and enhances transfer. Blocked practice groups all problems of type A, then all of type B, then all of type C. Interleaved practice mixes them. A, B, C, A, C, B, and so on. Research shows interleaved practice produces better long-term performance, even though it feels harder during learning. Why does interleaving work? It forces the learner to discriminate between problem types and select the appropriate strategy. Blocked practice allows mindless repetition without deep processing of when to apply each method. Let me give a concrete example from physics education. Suppose a learner is studying mechanics, kinematics, forces, and energy. Blocked approach. Solve 20 kinematics problems, then 20 force problems, then 20 energy problems. The learner knows which method to use based on the problem set. Interleaved approach. Mix problem types randomly. The learner must first identify what kind of problem it is before solving. This builds diagnostic skill and conceptual understanding. Research shows that blocked practice yields 85% accuracy during practice but only 60% on a delayed test with mixed problems. Performance collapses when learners cannot rely on context. Interleaved practice yields only 70% accuracy during practice, but 75% on the delayed test. The initial difficulty pays dividends in long-term retention and transfer. One major challenge for AI tutoring systems is detecting shallow understanding. Learners can sometimes give answers that sound correct but reveal fundamental misconceptions upon deeper probing. Example: a learner might state Newton's second law as force equals mass times acceleration, and define each variable correctly. This seems adequate, but does the learner truly understand? The AI probes deeper. What happens to acceleration if the mass of an object doubles while the applied force remains constant? A learner with shallow understanding might hesitate or answer incorrectly. From F equals ma, we get equals F over m. If m doubles, a is halved. But learners often memorize F equals ma without internalizing the inverse relationship between m and a. Follow-up question: how does this relationship explain your everyday experience? Why is it harder to push a heavy shopping cart than a light one with the same acceleration? The learner must connect abstract formula to concrete experience. The AI can employ Socratic questioning, a method where the teacher guides the learner to discover insights through carefully crafted questions rather than direct instruction. Instead of explaining why a misconception is wrong, the AI asks questions that lead the learner to recognize the contradiction themselves. This produces deeper, more durable learning. Example: a learner might believe heavier objects fall faster. Instead of saying that is wrong, ask: if two objects are dropped in a vacuum, which falls faster? The learner might predict the heavier one. Then show experimental evidence that they fall together. Ask: why might that be? The learner struggles, considers their assumptions, and eventually realizes that gravitational acceleration is independent of mass. This self-discovery is far more powerful than being told the correct answer. What is the empirical evidence for AI interrogation systems? Several studies have tested these approaches with promising results. Kai and colleagues in 1994 showed that prompting students to self-explain physics problems dramatically improved learning outcomes. Students who explained their reasoning learned more than those who simply practiced. Roediger and colleagues have demonstrated the testing effect across multiple domains: vocabulary, history, science. Testing consistently outperforms additional study time. Recent AI tutoring systems using adaptive questioning showed 20 to 40% improvement in learning outcomes compared to control groups with traditional study methods. These are substantial effect sizes. Effect size D equals the difference in means divided by pooled standard deviation. Effect sizes of 0.5 to 1.0 are considered large in education research. AI interrogation systems are achieving these levels. Despite promising results, current AI interrogation systems face several challenges and limitations. Let us be rigorous about what they cannot yet do well. Challenge 1. Understanding nuanced partial answers. Natural language is ambiguous. A learner might give a partially correct answer that requires human judgment to evaluate. Current NLP models sometimes miss these subtleties. Challenge 2. Maintaining engagement over long interactions. AI-generated questions can become repetitive or lose the narrative thread. Human tutors excel at weaving questions into a coherent story. AI systems struggle with long-term coherence. Challenge 3. Adapting to diverse learning styles. Some learners prefer visual explanations, others prefer mathematical formalism, others prefer concrete examples. Current systems have limited ability to detect and adapt to individual preferences dynamically. Challenge 4. Avoiding over-reliance on pattern matching. Transformer models excel at pattern matching but may lack true causal understanding. They can mimic good questioning without understanding why certain questions are pedagogically effective. Looking forward, what are the promising directions for next-generation AI tutoring systems? Direction 1. Multimodal interaction. Combine text, speech, diagrams, and interactive simulations. Allow the learner to draw, annotate, and manipulate visualizations while the AI provides guidance. Direction 2. Effective computing. Use computer vision and physiological sensors to detect learner emotions like frustration or boredom. Adjust pacing and difficulty in response to affective state, not just cognitive performance. Direction 3. Causal models of learner knowledge. Move beyond correlational models to causal models that understand why a learner holds certain beliefs. This enables more targeted interventions addressing root misconceptions. Direction 4. Collaborative learning with peer AI agents. Create AI agents that act as learning partners, not just tutors. The learner and AI can work together to solve problems, with the AI modeling collaborative problem-solving behavior. Future learning environments might include multiple AI agents, a tutor AI that asks questions, a peer AI that collaborates on problem-solving, and perhaps even a student AI that the human teaches, reinforcing their own knowledge. We must also consider ethical implications. AI interrogation systems collect detailed data on learner knowledge, misconceptions, and cognitive patterns. This raises privacy concerns. Data privacy. Who owns the data generated during learning? The learner, the AI provider, or the educational institution? Clear policies are needed to protect learner data from misuse. Algorithmic bias. AI systems trained on biased data may perform unequally across demographic groups. We must rigorously test for and mitigate bias to ensure equitable access to effective learning tools. Learner autonomy. There is a tension between AI guidance and learner autonomy. Over-reliance on AI tutors might reduce learners' ability to self-regulate and direct their own learning. Systems should foster, not replace, metacognitive skills. Let me conclude by synthesizing what we have covered. The fundamental insight is that reading is necessary but insufficient for building capability. Information must be actively processed, retrieved, applied, and integrated. AI interrogation systems provide the scaffolding for this transformation. By asking targeted questions, forcing application, and requiring teaching back, they convert passive consumption into active engagement. The cognitive mechanisms are well established. Retrieval practice strengthens memory traces, spaced repetition optimizes long-term retention, and interleaving builds discrimination and transfer skills. The neurobiological basis involves synaptic plasticity, hippocampal pattern completion, and systems consolidation from hippocampus to neocortex. Active learning engages these mechanisms more effectively than passive reading. Empirical evidence shows substantial learning gains, with effect sizes of 0.5 to 1.0. Time to mastery decreases by 30 to 50%, while long-term retention improves dramatically. Challenges remain in achieving truly nuanced understanding of learner knowledge states, maintaining engagement, and adapting to diverse learning preferences. These are active areas of research. Future systems will be multimodal, effectively aware, and support collaborative learning with AI peers. They will move beyond simple question answering to become true learning partners. The ultimate goal is not just to improve test scores, but to cultivate lifelong learning capability. AI interrogation systems, used wisely, can help learners become more effective at acquiring and applying new knowledge throughout their lives. Thank you for your attention. This concludes the lecture. I welcome any questions about the concepts, methods, or applications we have discussed.